in an automatic transmission. It's designed to connect and transfer power from the engine's crankshaft to the transmission input shaft. Hi, I'm Clint. The torque converter sits between the engine and transmission and is in effect a fluid clutch system. It automatically engages and disengages crankshaft torque to the transmission input shaft based on engine speed alone. A thin metal drive or flex plate, which is attached to the engine's crankshaft, serves two purposes. It provides a mounting point for the ring gear, so the starter motor can rotate the engine, and it provides a mounting surface for the torque converter housing, so engine torque can be transferred from the crankshaft into the converter and transmission fluid pump. Although it appears to look like one piece, the torque converter is made up of several smaller components. The impeller forms one section of the converter housing and is constructed with numerous angled blades attached between a guide ring and the inner converter surface. The impeller is the pumping or driving member of the torque converter. The outer housing of the impeller is manufactured with a hollow support shaft that has some form of machine locking mechanism used to drive the transmission fluid pump. The stator or reactor is a part of all newer torque converters, and it's designed with blades that are similar to that of the impeller. Just like the impeller, the stator blades are formed around part of a guide ring, which also matches the one in the impeller. The stator assembly has an inbuilt sprag or one-way clutch, which allows the stator to rotate freely in the direction of engine rotation, but prevents rotation in the opposite direction. When assembled, the stator slides over and is mounted to the transmission fluid pump reaction shaft. The turbine assembly looks similar to the impeller, with its angled blades and section of the guide ring. Where the turbine differs is in the fact that it is a rotating component within the torque converter and is not physically attached to the outer case. The turbine blades generally have a more aggressive angle than the impeller. This is due to its function as the driven member of the converter assembly. The turbine is attached to the transmission input shaft through means of a splined hub. This is similar in function to a manual transmission's friction clutch plate. Just like a conventional friction clutch, the torque converter lockup clutch also has a splined centre hub, torsional vibration springs, and an outer friction disc. The hub mates with the transmission input shaft and sits directly between the turbine and torque converter front housing. The housing has a machined face to accept the friction disc when engaged. Be aware that not all torque converters are fitted with a lock-up clutch assembly. When we accelerate in an automatic vehicle, there are quite a few things happening within the torque converter. These operations change based on speed and load conditions. We can break this operation down into 4 phases: idle, acceleration, cruise, and finally coupling or lockup. When we start the vehicle's engine, rotation of the crankshaft through the flex plate and torque converter drives the transmission fluid pump. Fluid is drawn through the pump and pushed into the torque converter housing. Once a predetermined volume is reached, oil flow continues through the transmission cooler and returns back to the valve body and pan. Fluid fill of the converter only occurs if the converter is dry. That is, if it's been replaced with a new one, or if it's been drained as part of a service or repair. The fluid in the converter is pushed to the outside of the impeller due to the centrifugal force caused by the converter's rotation. The relatively slow rotational speed keeps the fluid on the outer section of the impeller only. The fluid tends to rotate in the same direction as converter operation. This is known as rotary flow. With the driver's foot on the brake pedal and the gear selector moved to a forward or reverse position, there is no movement of the vehicle tail shaft, transmission main shaft, or input shaft. This means the turbine is also held stationary, while the impeller and housing rotate with the crankshaft. When we release the brake and press the accelerator, the crankshaft speed will increase in proportion to our demand. With a higher rotational speed influencing the converter housing and impeller, the fluid is pushed through centrifugal force around the curved impeller and through the blades. This action is the beginning of what we refer to as vortex flow. The fluid hits the turbine blades with enough force to drive the turbine in the same direction as the impeller. With increased engine speed, the turbine rotates faster, and because it's attached to the transmission input shaft, the vehicle moves in the direction selected by the driver. There is, however, a fundamental problem with the way fluid moves within the torque converter. If we look at the direction the fluid is travelling as it leaves the turbine blades, it tends to restrike the impeller at 90 degrees to impeller rotation. Unfortunately, this fluid action works against the impeller, slowing it down and robbing precious torque from the crankshaft. This is where the stator comes into play. It's designed to help eliminate this problem and act as a torque multiplier. During an acceleration event, the engine speed, and therefore impeller speed, is high, but the turbine speed is relatively slow. The fluid exiting the slow-moving turbine strikes the angled stator blades, applying force to the stator in the opposite direction of impeller rotation. This action locks the one-way, or Sprague clutch, to the pump's reactor shaft. The stator blade angle redirects the fluid so that it travels in the same direction as the impeller's rotation. The fluid then re-enters the impeller, providing additional force to the rotating blades. By combining this additional force with the rotating crankshaft and impeller, the total torque output applied to the turbine and transmission input increases significantly. This torque multiplication only occurs when there is a reasonable speed differential between the impeller and turbine. At some point, the driver will reduce demand for acceleration and ease off on the pedal. This generally occurs under cruise throttle conditions. With a lower crankshaft speed, the impeller's rotational speed is also reduced. With a lower speed differential existing between the impeller and turbine, there is, in effect, less fluid pressure acting on the stator blades, which in turn releases the Sprague clutch. The stator will begin to rotate in the same direction as the impeller and turbine, which results in a reduction of the torque multiplication effect. When we look at the torque converter operation during this period, we can see that the impeller and turbine speed are very closely matched. However, because the converter uses a fluid coupling, there will always be some slip between the two. In most torque converters, this can still be as high as a 10% difference. Slip between the driven and drive members is an equation for excessive fuel consumption. So, most torque converters are fitted with a lock-up clutch. These converters have some additional space between the turbine and the front impeller housing where the clutch is located. When drive conditions favour torque converter lockup, high pressure fluid is sent from the valve body to the rear of the clutch disc. The friction disc is forced against the converter's outer housing, effectively locking the transmission input shaft to the impeller. This locking action eliminates any slip occurring between the two. Torque converters do fail, whether from poor quality or contaminated fluid, one-way clutch seizure or collapse, or just general wear and tear. It's important to know how this part operates, so that when we need to perform diagnosis, we can do so correctly and with confidence. As always, keep training. Thanks for watching.